Good morning, dear student, and welcome to this second part of our overview lecture on Lebesgue theory. So, during our last presentation, we were talking about the measurability of a function defined from a given set x into another set y, where x and y are endowed with two sigma algebra, respectively, calligraphic A and calligraphic F. And we saw that a function or a mapping F defined from the measurable space X endowed with the sigma algebra calligraphic A into the measurable space Y endowed with the sigma algebra calligraphic F is measurable or immeasurable if for any element of the sigma algebra F, the pre-image of A is in the sigma algebra A. So A is what we can call the source sigma algebra because it's a sigma algebra on the source space, and F is the destination sigma algebra because it is a sigma algebra over the destination set Y. So we saw that this is equivalent to say that the pre-image of a measurable set of Y, because A here is a measurable set of Y, is a measurable set or subset of X. And in the particular case where the destination set Y is equal to R, the number line, we can take its corresponding sigma algebra calligraphic F to be the Borel sigma algebra of R. Because each time Y is R, we can always take the default Borel sigma algebra to be the Borel sigma algebra of R. And in this case, for the Borel sigma algebra of R, we can always characterize measurable sets. So our F here, which is the Borel sigma algebra of R, can be characterized by such a set, the set of X so that f of X is greater than A. And if we vary A, this would generate what we can call a basis of the sigma algebra. So this is possible because of what we indicated in the previous slide during the last lecture. So we are going to go back to see how we can characterize a basis of a Borel sigma algebra over R. So from this slide, we saw that any of these sets can be used to characterize the Borel sigma algebra of R. In this case, we can see that X is equal to R. And we saw that the Borel sigma algebra of R can be generated by any of these collection of subset of R. And particularly if we target C4, which is the set of interval of the form A infinity, where A is in R. So if we rewrite C4, we know that we can also write our Borel sigma algebra of R to be the sigma algebra generated by C4. So in that case, we can take element of this form to characterize an element of our Borel sigma algebra on R. And that is exactly something similar that we have here in this proposition. Okay, so coming back to what I was talking about, we say that we can take our sigma algebra to be the Borel sigma algebra of R, and we see that this can also be written as the sigma algebra generated by C4, right? Where C4, as we saw, is the collection of open interval of the form A infinity, where A is an element of R, like this. Now, if we take an element of F, meaning that it will be, we can take an element of this form, because that sigma algebra is generated by C4, meaning that it can be an element of this form. Now, our capital A, in this case, can be taken to be this element. So we take our capital A to be A infinity. So if A is an arbitrary element of R, we have an element of the Borel sigma algebra. Because an element of C here, such an element can be considered to be an element of our Borel sigma algebra. Why? Because the Borel sigma algebra contains C4, right? Because the definition is the smallest sigma algebra containing C4. So if it contains C4, it contains each element or all the element of C4. So meaning that element of this form will be in the Borel sigma algebra. Now, how are we going to write the pre-image of A? The pre-image of A will be, from here, we take the pre-image of this interval. We say that it will be the set of X, element of R, such that f of X is greater than A. Why is it greater than A? If f of X is in this interval, to write that f of X belongs to this interval, A infinity, it is equivalent to say that it is in between A and infinity. Obviously, this part is always true, so we will write this part. F of X strictly greater than A. Right. So we have a good characterization on how we can prove that a function whose range is contained in R is measurable. Right? If you want to show that a function taking its value in R is measurable, we will always consider an interval of this form. So it can be this one, or it can be any of these set, right? In the proposition. So we have the first, we have the second, which is similar, the third, and so forth. So it's equivalent to use any of them. Okay. So I think having set the stage, we can proceed, right? So this proposition states that if f is a real value function, the following conditions are equivalent. So remember what we said here, that a function is measurable if this set is an element of calligraphic A for any A in R. So we can use this set or any equivalent set given by this proposition. So there are cases whereby this will be the convenient way, f of s strictly greater than a, or we can use the case where f is less than or equal to a, or strictly less than a, or greater than or equal to a. So it's equivalent to use any of them, and we can prove that the function is measurable if this or one of these equivalent is true. For any a, the set is an element of calligraphic A, right? So it's a good characterization that is worth considering. Okay, another proposition. If X is a metric space, A contains all open sets and F, defined from capital X into R, is continuous, then F is measurable. So if you recall how we define continuity in a topological space, it is exactly equivalent to the definition of measurability. So meaning that if a function is continuous, we will write exactly the same definition, which will correspond to measurability. So this was mentioned in class. So the next proposition, if C is an element of R, and we assume that F and G are two measurable real value function. Real value function means that we can consider a representative of the sigma algebra to be set of this form. Because for any real value function, as we already indicated, you can use any interval of this form. Good. So we have f and g from the proposition to measurable real value function. Then the sum of two measurable functions, the negate of a measurable function, a constant multiple of a measurable function, the product of two measurable functions, the max of two measurable functions, or a finite, or the max of finite sets of measurable functions, because if something is true for two measurable functions, it will also be true for a finite set of measurable functions. The minimum of two measurable functions, or the minimum of a finite set of measurable functions, are also, so these functions are also measurable functions. So I repeat the proposition. If we have two measurable functions, f of f and g, their sum, they negate, constant multiple, the product of the two measurable functions, the max of the two measurable functions, and the minimum of the measurable function are all measurable functions. We are not proving this, but we are just in this overview class, give the result that will be useful for the continuation. The next proposition, if f of k is a measurable function, right, and f is a real value function for each k, so meaning that we have actually a sequence of measurable functions for each k, then so are the following: the supremum of this measurable function, the infimum of these measurable functions, the limit superior of this measurable function, the limit inferior of this measurable function are also measurable. Obviously, provided that these values are finite, meaning that they are well defined. Because if the supremum gives you infinity, you will not say that infinity is a measurable function. So provided, no, sorry, not measurable function, but yes, measurable function. Okay. The next definition, we say that a function or two functions, f and y are equal almost everywhere. And we write f is equal to a, f is equal to j, ae. A stands for almost and e everywhere. It's just an abbreviation. So two functions f and g are equal almost everywhere if the set of elements where they are different is null or is a null set. So meaning that the measure of such a set is 0. Similarly, we will say that a sequence of function fk converges towards f almost everywhere if the set of elements where, or the set of point x, where fk of x does not converge towards f of x is a null set. Now, if we assume that X is a metric space and B is the Borel sigma algebra, and if we consider a function f defined from the metric space X into R, so if we assume that that function is measurable with respect to the Borel sigma algebra of R, of course, we say that f is Borel measurable. Besides, if f is defined from R into R, meaning that in R we have our Borel sigma algebra and also in X we have the same Borel sigma algebra, such a function is measurable with respect to the Lebesgue sigma algebra. If that is the case, we will say that f is Lebesgue measurable. Let me specify what I said here about the B. In the case where we have X, where X is a metric space, this B is not the Borel sigma algebra on R, but actually it's the Borel sigma algebra on X. Because X being a metric space, we can define a topology on X by open sets. And this B will be the Borel sigma algebra of X. Now for R here, we will consider the Borel sigma algebra of R, meaning that we have two measurable spaces. The spaces made of X and the Borel sigma algebra on X, and the measurable space made of R and the Borel sigma algebra on R. So this is, I think I said something that was not correct and I realized it, so that's why I'm correcting. Okay, the next proposition. If f is a function defined from R into R, is a monotonic or a monotone function, then f is Borel measurable. So any monotone function defined from R to R is Borel measurable. And we can only talk about Borel measurable function when the source space is contained in R and the destination space is contained in R, or is R, or are R. So a function defined from R to R, which is measurable, is called Borel. It's called a Lebesgue measurable function. Okay, so we are going to define what we call a characteristic or indicator function of a set of X, where X is a measurable space. By that, I mean that X is endowed with a sigma algebra calligraphic A. So any element of A, any element E of calligraphic A, for any element E on in the calligraphic A, we can define its indicator or characteristic function. 1 sub A sub E of X takes the value 1 if X is in E and the value 0 if X is not in E. And then from indicator function, we can define what we call simple functions. So S is a simple function if it is of this form. So it's a fine or a linear combination of characteristic or of characteristic function of measurable set EKs. And we know that a measurable set is an element of a sigma algebra. So meaning that we assume that all these EK are element of this of the sigma algebra calligraphic A. So what is the purpose of defining characteristic function? This will allow us to define the measure or the integral, right, of a simple function. And from this one, we'll be able to construct the integration theory. So proposition. We suppose that f is a non-negative function, which is also at the same time measurable. So f is a non-negative and measurable function. Then there exists a sequence of non-negative measurable simple function x s sub n increasing towards f. So we have an increasing convergence of this sequence of simple measurable function towards the function f, which is a measurable function. So in other words, we can always approach a measurable function by measurable simple function. And the proof is given as follows. So we define AKN to be the set of element x such that f of x is sandwiched between these two values. And Bn is defined to be the set of x such that f of x is greater than or equal to n. Of course, for n taking the value from 1 up to infinity. So it's a sequence of sets. And k takes the value, see, k is defined here, takes the value 1, 2, up to 2 into 2 to the, k takes the value 1, 2, 3, up to, the last one is n into 2 to the n. And we can define, from these two sets, we can define our simple functions Sn to be the finite sum of this indicator function. That is, so this indicator function here, each indicator function here would take the value k minus 1 by 2 to the n when x is in akn. Akn is given by this. So if x is here, the simple function would take this value. And if x is in Bn, it will take the value n. So this is how we define our sequence of simple function. We know already that this is a simple function, right? Because it's a finite, it's a combination, a linear combination of indicator function. And this is another indication function. So this gives us a sum of indicator function. So this is a simple function. So in other words, Sn takes the value n, right? If x is greater than or equal to n. F of x greater than or equal to n means that x is in Bn. And it will take the value if f is sandwiched between these two values, meaning that x is in A, Kn. So it is easy to see that Sn has the desired property. That is, it converges increasingly towards the function f. So first of all, increasingly means, first of all, that this sequence is an increasing sequence of functions. So this is easy to see. And we can show that it converges point-wise towards f. So now we are going to define the integral of measurable function. So we have a measure space given by the triplet x, calligraphic A, and mu, right? Meaning that A is a sigma algebra on x, and mu is a measure defined on calligraphic A. If S is represented, it's a simple function represented by this expression, and if we assume that all the AKs are positive, this defines a non-negative measurable simple function. And from this, we can define the Lebesgue integral of S. So that is the definition of the Lebesgue integral of a simple function, measurable simple function. And this function is measurable because the EKs are in the sigma algebra. So we know that if the EKs are in the sigma algebra, this is equivalent to say that the indicator function is measurable. And if it's measurable, you remember from one of the previous proposition, if this is a measurable function, and let's say we take our f to be that indicator function, and we take c to be AK. We know that a constant multiple of a measurable function, in this case AK, the indicator function of EK, this is measurable. And we also saw that the sum of two measurable functions is a measurable function. And I extrapolated by saying that if it's true for two, it's true for a finite number. So this finite sum of measurable function is also measurable, right? So that's to justify this statement of S being measurable, right? Okay, so it is important to specify all these. Since we just defined those various concepts, it's always good to stress on that. So for a measurable simple function, we define the integral with respect to mu of a simple measurable function to be the finite sum of AK mu of E sub k. So if I have a measurable function in this defined by this expression, its Lebesgue integral is given by this expression, given by equation 5. So this definition is given with the convention that AK mu EK is 0 if AK is 0 and mu ak is infinity. So in other words, we are assuming that the product of 0 and infinity is 0. So it's a convention. We set it like that. Remember the definition of a measure? We say that a measure takes its value from 0 to infinity included. So the measure of a set can be infinity. So if it is infinity and it happens that the coefficient is 0, how do we define the product 0 infinity? So by convention, we set that product to be 0. So it is important to bear that in mind. Okay, so now that we know how the integral of a measurable function is defined, that is a simple measurable function is defined, we can now define the integral of a measurable function. This is important to first define the integral of a measurable or measurable simple function, because as we know from the previous proposition, this one, we saw that if f is a non-negative measurable function, we can always find a sequence of simple function Sn So if f is measurable, we can always find a sequence of simple measurable function such that Sn converges towards f, right, when n goes to infinity. So if we are able to define the integral of simple function, we'll be able to use that to define the integral of f itself by approximation, right? So that's why it is important to first define integral of simple function, knowing that for a measurable function, we can find such a sequence of measurable simple function that will converge towards f. So this being said, if I have a non-negative measurable function, we know already that such a sequence exists, right? So the integral of f will be taken to be what? The supremum of the integral of simple measurable function, where we take the simple measurable function to be less than or equal to f. We know already that such a measurable, such a sequence of measurable or such measurable function, simple measurable function exists. So if they exist, it means that this set is non-empty, because we can always find such measurable function. And it's worth mentioning that this convergence is an increasing convergence. The sequence of measurable function is increasing towards f. If it's increasing towards f, what does that mean? If I increase towards something, it means I'm below the thing. So already from here, we can say that this set is non-empty. Obviously, we are not sure whether the supremum of this is finite. We are not sure. We are not sure that the supremum is finite. It can be finite, it can be infinity. Right? So in this definition, this is just a definition, but this definition does not specify that this integral is finite. It just gives us a definition. How do we define the integral of a positive or non-negative measurable function. This is how it is defined. Now, the case whereby the integral will be finite, we will tackle that case. Okay. Now, if our function f is no longer positive, meaning that it has an arbitrary sign, how are we going to define its integral? Because that's the ultimate question. So, for any function that is not positive, a function that has an arbitrary sign, we can always define an arbitrary function f to be the sum of its positive part, or I mean the difference of its positive part and its negative part. So each of these functions, f plus and f minus, they are both positive, right? And what is f plus? F plus is the maximum between the function f and 0. So this is always positive because it's greater than or equal to each of them, so it's greater than or equal to 0. And f minus is also the maximum between negative f and 0. So this also is greater than or equal to 0. So we take the difference between the two, it gives us f. So meaning that if f is negative, the maximum f plus from here, the maximum will be 0 if f is negative. So if f is negative, f plus will be 0. F will be 0, f plus will be 0. And in that case, f will be equal to minus f minus. But f minus is positive, right? With the negative, this will always be negative. It makes sense. But if f is positive, f minus, which is the maximum between negative f and 0. So if f is positive, negative f will be negative. And if it is negative, and I take the maximum between negative and 0, it will be 0. So this gives us f minus will be 0. And in that case, f will be equal to f plus, and f plus is positive. Now, if f takes negative value in some interval and positive in other parts of the interval, then f will be given by this expression, f plus minus f minus. So this shows that our expression is well defined. Okay. So we still know that our function f has an arbitrary sign. And we assume that it is measurable. Now, if the integral of the absolute value of f with respect to the measure mu is finite, then we say that f is integrable. This is important. In the previous slide, we defined the integral of a positive measurable function, but we were not sure whether it is finite or not. Now, if the function has an arbitrary sign, we can always write that function as the difference of positive function, f plus and f minus. So each of them are positive function. So if we want to define the integral of f with respect to mu, we will define that to be the integral So you see that if we reuse this definition, this integral is the integral of a positive measurable function. And this will be given by this supremum. And this other part, f minus, is also a positive measurable function. And its integral will be given by a similar definition. But the problem here is the negative sign in between. Because if each of them takes the value infinity, infinity minus infinity is not defined. So in order to avoid that, we will consider the integral of the absolute value, because absolute value of f, by definition, will be f plus f minus. This is positive, this is positive. The sum of two positive functions is always positive. Now, if you are able to prove that this sum is finite, we will conclude that the original function itself is integrable. So that's how we avoid dealing with something of this form. So, to summarize, a measurable function of an arbitrary sign is said to be measurable if the integral of its absolute value is finite. Okay. There is something that I did not say, or I did not stress on. What have I said here? I did not stress on the fact that f measurable implies that f plus and f minus are both measurable, right? Because to consider the integral of f plus and f minus, as I did previously, they have to be measurable function. So what I said previously will make sense if we are sure that they are measurable function. And this is the case. Why? Because by definition, f plus is the maximum between 0 and f. 0 is measurable, f is measurable. We saw in a previous proposition that the maximum of two measurable function is measurable. And we also saw the same thing. Okay, this will still be true. We saw that a constant multiple of a measurable function is measurable. So we take our constant to be negative 1. So f minus, minus f is equal to negative 1 times f. And this is our constant c. This is measurable. The constant times a measurable function is measurable. So negative is measurable. So I have negative f, which is measurable, 0, which is measurable, the maximum is measurable. So f plus and f minus are measurable functions. Therefore, we can define the integral of f plus and f minus. So that's something I needed to specify. I realized that I didn't mention that. Okay. So we are good to go now. We can now state the following proposition. The first result, if f is a real value measurable function and f is sandwiched between a and b for all x, and if beside we assume that mu of x is finite, then the integral of f will be sandwiched between a mu x and b mu x. Now, if f and g are two measurable functions, two real value measurable function, and if we assume that they are also integrable, sorry, let me rephrase that. If f and g are measurable, real value integrable, and f of x is less than g of x for any x, then the integral of f with respect to the measure mu is less than or equal to the integral of g with respect to the measure mu. And the last, no, not the last, second last, 3, if f is a real, if f is real and integrable, real mean real value, and c is a real or complex number, then the integral of the constant multiple f cf with respect to mu is equal to c integral of f d mu. Of course, we know these properties for Riemann integral, right? But here we are extending those properties that we know already for Riemann integral. We extend them to Lebesgue integral. The last proposition, I mean the last bullet of the proposition, or the last property, is if the measure of A is 0 and if f is integrable, the integral of the product of f with the indicator function of A, which by definition is the integral of f over or along A, d mu is 0. Theorem. Let f be a bounded real value function on I, the closed interval AB. If f is Riemann integrable on I, then f is Lebesgue measurable and Lebesgue integrable on I, and moreover, the integral, the definite integral from a to b of f of x dx will be the integral of f with respect to d mu over I. So in other words, we are defining, actually we can summarize this proposition to say that if f is Riemann integrable, it implies that f is Lebesgue integrable. Now, how do we write the Lebesgue integral of the function x in terms of its Riemann, how do we write the Riemann integral of the function f in terms of its Lebesgue integral? And that is what this formula gives us, because we know that this is the Lebesgue integral. So this, by definition, will be the characteristic function of the closed interval AB, like this, d mu. And we know that this, by the previous result, from this fourth property of the proposition, if I have the integral of a product of this form, you see that the second function in the product is the characteristic function of a set A. Then the integral will be along that set, right? So that's what we use here. So it will give us the integral, the Lebesgue integral of the function along the set A, which is the closed interval AB, and F this. And this is what we denoted as the integral along I, because this integral, this closed interval A, B is I. So if we rewrite that, we will say that is the integral over I of F d mu. So that's how we connect Riemann integral to Lebesgue integral. So we just stated the result of the theorem that if F is Riemann integral, integrable on I, therefore it's Lebesgue integrable on I. But the reciprocal is not true, meaning that we can find functions that are Lebesgue integral, which are Lebesgue integrable, but not Riemann integrable. And for that, remember I mentioned this in the beginning of the overview lecture, the Dirichlet function. We saw that, we say that, I stated, but we did not prove it. We are going to see why this is not Lebesgue, it's not Riemann integrable, and why it is Lebesgue integrable. So already you can see that this is a characteristic function, right? It's a characteristic function of this set, Q intersection the closed interval 0, 1. So we know already how we can write that integral in terms of the Lebesgue. So we can because this is a simple function, right? This is a simple function. So the integral of the Dirichlet function with respect to mu will be the integral of the simple function Q intersection the closed interval 0, 1 d mu. And remember, if you have the integral of a simple function of this form, the value here in front is 1. So it's 1 times. And we saw that it will be equal to this coefficient times the measure of the set. So it will be 1 times the measure of the set Q intersection So now the next thing is to compute this. Okay, so we know already that Q, we can write Q, this was specified, this was mentioned previously, is the set of singleton R for rational, right? I can take the countable union of elements of Q. So this will give us, now if I take this Q intersection, this closed interval, I will be able to write Q intersection, the closed interval, so in other words, in this closed interval 0, 1, I will take all the rational numbers that are in between, right? So this will give me the union of, we will call that R prime, singleton R prime, where R prime is in Q and R prime is in between 0 and 1. This is a countable union because R is countable. It's a countable set. Now, if I write, we know already mu being a measure, we know by definition that this mu Q intersection the closed interval 0, 1. This will give us mu of this set. I will just replace with the sum or the series, because this will give us a series, mu of such a singleton. Obviously, the sum, we take that sum over all these elements of Q between 0 and 1. But this measure, the measure of a singleton, is 0. Why is it 0? Because this mu of the singleton R prime will be equal to the measure of the closed interval R prime, which has only one element. And we know already that the Lebesgue measure of such interval is just the length of the interval, R prime minus R prime, which is 0, right? So with this, we can conclude that the integral of the Dirichlet function is 0. So it's integrable. It's finite, so it's integrable. It's integrable. So it's finite, so it shows that because the absolute value, being the function being positive, absolute value will give us exactly the same result. So if I want, I can put it here. So it is finite. This is Lebesgue integrable. Now, why is it not Riemann integrable? That's what we need to figure out. So we can take a partition, an arbitrary partition of the interval AB, because remember how we construct the Lebesgue, the Riemann integral. If we integrate along an interval, in our case, we are integrating along 0, 1. So we take a partition of the interval of integration, we partition it. So that's what we are doing here. And we construct the lower and the upper Riemann sum for that partition. Okay, so we define LPF, the lower Riemann sum, and UPF, the upper Riemann sum, as follows. The lower Riemann sum will be the sum along K of MK delta K, and the upper Riemann sum will be the sum over K of capital MK delta K, where delta K is just the length of each subinterval of the partition. That is absolute value of xk minus 1. So that would be the length of the subinterval ak minus x sub k minus 1 xk of the partition. And lowercase m sub k will be the minimum of the function over that subinterval. And capital M sub k will be the maximum of the function for x over the same subinterval. So because x, our sigma, sigma chi, the Dirichlet function takes only two values, 0 and 1. In each of these subinterval, we know that we will always find, because Q is dense. So we will always find a rational number between each subinterval of the form x sub k minus 1 xk. We will always find a rational and irrational number. So, meaning that our m sub k in each subinterval, which is the minimum, will be 0 because it takes only those two values, 0 and 1. So the minimum will be 0 and the maximum will be 1. So if we sum 0, the result is 0. But now here, if we sum 1, because all these will be 1, so for the upper Riemann sum, okay, we can first of all already conclude that the lower Riemann sum will always be 0. And the upper Riemann sum is not actually 1. It's finite, but it's not exactly 1. This one. The upper Riemann sum is not exactly 1. Look here. All the MKs here will be 1. Now, if you substitute here, delta K, you can see that the delta K is this difference. And if you have a large partition, this will be small. It will be less than 1 anyway. It will be a smaller quantity, less than 1. Right. Okay. Now, if we take equal and we denote that by delta. Now, in this upper Riemann sum, because M is 1, it will give us the upper Riemann sum with respect to the partition will give us the sum of delta, this finite sum of delta over K. So since this is constant, we take it out. So that will be exactly N delta, N into delta. So that will be the value of the upper Riemann sum. But this is smaller, less than 1, as we saw here. It's less than or equal to 1, right? So this value will be less than or equal to N, and N is finite. So this actually, we will say that is less than or equal to N in the case where delta is finite. I mean, is constant. All the delta keys are constant. Even if they are not constant, I think we will still have something similar. Right. So what do we realize now? And this is non-zero. This is non-zero, right? It cannot be 0 because N is strictly greater than 0. So we have lower Riemann sum, which gives us 0, and the upper Riemann sum gives us a value that is non-zero. So this is non-zero. So what do we conclude? That the function is not Riemann integrable because the upper Riemann sum is different from the lower Riemann sum. And the function to be Riemann integrable, the upper Riemann sum and the lower Riemann sum should be equal. Right? I mean, the limit of the upper Riemann sum and the lower Riemann sum when n goes to infinity should coincide. So the both should coincide. So if in our case they will not coincide, and because they are not coinciding, we conclude that is not Riemann integrable. But the Lebesgue integrable, as we already proved, the integral is 0. So the main reason the Lebesgue integral is much easier to work with than the Riemann integral is that it behaves nicely when taking limits. So in this subsection, we state, and we'll prove later on, 3 fundamental results everyone must know, namely the monotone convergence theorem, denoted or abbreviated by MCT, Fatou lemma, FTL, and the dominated convergence theorem, DCT. Dominated convergence theorem is also called, sorry, not the dominated, but I mean the monotone convergence theorem here is also called Bepo-Levy theorem. In some textbook, it's called Bepo-Levy theorem. So we are going to tackle that later on. I think we'll stop here for now because we have been recording for about an hour. So in order to shorten the video, I think we will stop here for now. And we will continue with the last part of this overview class. And I will do also some tutorials where we solve a few examples based on this theory. So I thank you for your kind attention. See you later.